Lovely. So this talk, what I'm going to be presenting today is very much a work in progress, especially the second half of it. So bear with me. What I'm interested in are these ocean gliders. If you aren't familiar with them, they're these devices that are programmed to swim through the ocean, or to fly through the ocean, as it said. So they of course are affected by whatever ocean currents there are, and then they're controlled to take some specific path and pop up somewhere else in the ocean. Along the way, they collect data, right? So they fly through the ocean on some programmed path. They surface and report back their collected data in transit. So they have no way, of course, to report it back through the ocean. When they come back up, they have a GPS, so they report back whatever data they've collected, and they get programmed for their next leg of their journey. And this is a sort of sequential process. Okay, so what does the data look like from these sorts of devices? Well, it's collecting all sorts of data as it goes down. I guess there's all sorts of sensors that can be put on these things. So they could collect biological data, chemical data, optical data, in addition to the sorts of things we normally think about wanting to know, like pressure, salinity, and temperature. And the data it's collecting is effectively a continuous three-dimensional spatial time series. So why I've been thinking about this is a couple months ago, I was visiting an ocean, or the Naval Research Lab in Stenison, Mississippi, and I asked them how they assimilate this sort of data, and they basically said they don't know what to do with it. So I'm paraphrasing, but effectively, they said they have this whole time series of data. What they do is they treat sort of the older data as if it just had more and more air, and that's what they use to incorporate it. Okay, so glider paths clearly depend on both ocean currents and the driven motion, so these things can be steered. And so this is a control problem. It's not what I'm going to be thinking about, but ultimately for the person steering it, it's a control problem that depends on the estimates of the ocean velocities. Okay, so we're looking for a sequential method that can handle nonlinear data. So I'll spend some time going over particle filters again. I know many of you have just seen me talk about this, but if it's new to you, it certainly doesn't hurt to see it again. And then I'll talk about what I'm proposing, and really what I'm proposing is both sort of a test problem and a potential method, neither of which I think I've really ironed out quite yet, but it's a first go at it. So this test problem is a point vortex system, which we'll talk about, and I think you'll hear more about today. And we'll talk about the strategy I'm using for semi-Lagrangian. So I'm calling it the semi-Lagrangian data assimilation because it's both steered and is moving with the ocean currents. And that'll be a Brownian bridge. Okay, so I think we're all sort of very familiar with this scheme, right? I think maybe Chris had this exact slide in his first talk. And I think my hair is making noise on the mic. And so we're thinking about updating our system sequentially, and really how we obtain these distributions on the right-hand side is what we've been talking about for a week, right? There are all these different methods. It sort of depends on what your goal and what your computational power and what your skill is, what you choose. Okay, so we're going to think about particle filters. So let's sort of think through this, this definition of a discrete probability distribution. So a discrete approximation to a continuous distribution is typically what we're thinking of. So I'm looking at the probability of state xj given all the observations before time j. And what happens is at the previous time, we have some posterior distribution for the weights of our states. The states themselves, they get moved forward according to some model. Here I'll think about it being a stochastic differential equation. But they hold on to their weights. So the posterior weights at one time step become the prior weights at the next time step. And that's this blue distribution here. So this is sort of color-coded. So red means posterior. So this is the posterior at the previous time step. And this is the distribution, the prior at the current time step. Right, so we have this picture where each of these becomes one over here. So its state updates according to some model, and it holds on to its weight. All right, so let's look at a cartoon of this sort of an action. So we know our prior distribution. We're going to use Bayes' rule to update and get our posterior distribution. To use Bayes' rule, so we already have our prior, we need a likelihood, which of course is just whatever our H function is, our observation operator, how close that is to the data. Right, so I have my prior distribution, the observation. Now what happens, of course, is most of the mass is going to be close to the observation, and it's going to be on the particles there that are already there. So they effectively get reweighted. So they don't move necessarily, but they get reweighted. And our posterior is then this product of the likelihood and the prior for each particle. Right, for each particle is what we're thinking about. And then we repeat the process. Okay, so I thought I had another slide, but that's okay. So here's our test bed problem. So it's pretty simple to write down. We're looking at this point vortex system. So we have two vortices. Here's their equations of motion. Effectively, each of them generates a rotating field around it, and the other one feels the motion of its neighbor's field. So these two vortices will move in a circle around each other if I'm perturbed, and their strengths are equal. If here's what a stream function of that picture looks like. So I just said they're moving around each other, and so we're looking at this co-rotating frame where we're on a camera moving at the same speed effectively. So in that frame of reference, these guys are fixed. And the stream functions would be exactly the path that a passive tracer would take if you dropped it in this flow field. So here are just a few examples of passive tracer paths for this stream function. So this is the model we're going to think about, and we're going to look at a stochastic version of it. So M is really incorporating all of these equations up here, and then we have some noise term. And this is, maybe a bit sloppy, but people think about using this to resolve to account for unresolved small scale effects. Okay, so let's think about Lagrangian data assimilation. So when the system is noisy, those vortices don't stay fixed. They take some random walk, and then they're feeling the pull of the other one, so they maybe take an interesting path. And the goal of this isn't to observe the velocity in the fluid field. It's to observe tracer locations where a tracer is being passively affected by this field. And we'll observe it just periodically in time. So here's sort of the whole time picture of one passive tracer. We would pick off a few elements at observation times, and those would be the truth plus some noise. And from those passive tracers, we'd like to infer the paths that the vortices took. Right? So this is the sort of game with Lagrangian data assimilation, that we make the tracer part of our state variable. Right? You're going to hear a lot more about this idea today, I'm pretty sure. Okay, and if we do that, right, so we're basically calculating our weights, updating with Bayes' formula, completely based on these tracer observations. But then those same weights are attached to all of the states for each particle, so we can get estimates of the vortex paths. So this is sort of the general setup in the passive case. Yeah?
The tracer equations are stochastic.
Right.
On top of it, you add the
Right. So the equations themselves are stochastic. Actually, in this yellow curve is too. It might not quite look like it because it's kind of a big symbol I plotted. But and on that scale, it's a little bit hard to see. But these equations themselves are stochastic, and then there's observation noise as well. Yeah. Okay, so I thought this slide should have been earlier. So I thought this was the one that was missing. So let me sort of go back and attach it to the particle filter. Sorry for this interruption. Okay, so we had our particle filter, and we proceed, but one of the big problems with particle filters is that all of the weight, after some iterations, all of the weight can collapse onto one particle. So then you're doing Monte Carlo with the number, with one sample effectively. So that's not, it's clearly not good. So the idea to deal with this is sort of now a well-tested, well-studied idea called resampling. So basically, what we're going to do is, if we have some sort of detection, we'll put in some, typically you'll put in some sort of criteria that if too much of your weight is on too few particles, employ resampling. So here, we're thinking about one way to do it. There's plenty of ways to do it, but this way makes sense, I think. So here are our states. Right here were the ones with the most mass, so those are the ones we're effectively going to be resampling. And what I can think about is multiplying the weights of those red states by the total number of particles. So the state with the heaviest weight, well, he'll have 15 copies in this new distribution. Right, and then the ones with pretty decent weights will have 5, 4, 3 copies. And so we're sort of resampling the main mode of this posterior distribution, and because this is a stochastic system, right, it's okay to put in 15 copies of one guy because the noise in the system will spread them out. So this is sort of a standard scheme. And sorry about its misplacement. Okay, so the semi-Lagrangian data assimilation idea. So it's a sort of a one-step ahead approach, because we're going to know where the glider surface is, right? It's going to come up and say, I'm here. It's going to presumably come up somewhere different than we told it to come up, because it didn't have a perfect prediction of the currents. So the actual glider path and the proposed glider path will likely differ, because the proposed one was based on some forecast of the velocity field. And then, of course, the surface location will be different than the one that was originally targeted by the person driving this vehicle. Okay, so we want to sort of know how to use this time series nature of the data between surface things. This isn't something I actually think I'm doing well yet, but this is something I want to do. Right, and our scientific goal is, of course, to recover the actual path, and then to hopefully in the process provide velocity forecasts for the next step. So this process can just be repeated over and over for several flights. Right, so my current objective is less lofty. It's to identify a nice test problem and to come up with a data assimilation strategy to deal with this sort of flavor of data. Okay, so here's a passive tracer in the noiseless case, one where it wasn't driven and it just followed the path on the stream function like it would, and one where it was driven by some function A in addition to the underlying current. Okay, so A is some steering function. We're not going to right now worry about where it comes from, but for our test problem, we're thinking about, that's an interesting problem in its own right, I think. But for this test problem, we're just going to think about it maybe being like a rotation matrix that could sort of steer you, move you in different directions. Okay, so and sort of the idea here for the particle filter is that all of the particles are going to be driven in the same motion, But each of them is going to have their own estimate of the velocity field. Each particle has these vortex locations associated with it. So they're all going to be moving differently. Right, so this A part's the same, the rest is different.
Is that prior to the one?
Is that?
The equation each side equals I over the one?
Yeah, it is, and I was probably sloppy with including an I or not there.
So it's complex.
It's complex, yeah. Okay, so how to assimilate this this data? Yeah. Right.
So they are the same for all the particles?
No, each particle has its own vortex location.
That particle you mean each glider or each one for each one?
The glider has some true one that we don't know, and each particle has its estimate of the gliders, which is unique to the particle. Okay. Other questions?
So this can be singular?
Yes, so it is singular if you're close to, obviously if you're very close to the vortex. Yeah, and sort of in practice, you don't end up on top of it, but if you end up very near one, you're going crazy in a circle about it. And that's very hard on basically any data assimilation scheme, but certainly on something that's linear. Okay, so here's the idea, I guess, that we're going to observe these surfacing locations, and these are going to be our target for our data assimilation. So we know that we come up over here. We'd like our particles to take a similar path and come up close to the surfacing location. Right, so in some sense, this is kind of like a one-step smoother, right? We're going to use this information and go back and see what these paths look like. And this is sort of very similar in spirit to a couple things recently proposed by Van Leeuwen, which he calls efficient particle filters, and by Chorn, which he calls implicit particle filters. And there are 2 or 3 recent references on each of them. And the idea I'm going to talk about is to use a Brownian bridge to try to get our particles near the target. Okay, so here's the stochastic differential equation for a Brownian bridge. This picture we're looking at, we just have one x variable going up and down, and we're thinking about it over time. And so if this term wasn't here, this x variable would just be taking a little random walk, right? And basically what the Brownian bridge does is it says, well, wherever I'm at, I want to be there, so I'm going to push myself, in the drift term, I'm going to push myself on a line toward my target, right, is the basic idea. And so this is what we want to do, to use the surface location as a target, and then push our tracer paths with the Brownian bridge toward that target. So this is the plan. So the star there doesn't really mean anything. Sorry about that. So we're not actually going to solve the tracer equations we're given because we want to end up near the surfacing location. So we're going to add this Brownian bridge onto the drift part of our equation. Okay, so I sort of broken this up a bit, although I think the black and green are kind of hard to tell apart here. So the black is the motion due to the vortices. Again, that's specific to each particle. The control is shared by each particle, and it's some just pre-prescribed function in this case. And the Brownian bridge is also then unique to each particle, right? It's trying to move toward, each particle is trying to move toward the target.
Where is the Brownian bridge here?
Where?
In your equation, where is the Brownian bridge?
It's this first term here.
Oh, I see.
Yeah. And so we're going to end up sampling a process that's different than the true underlying process. And so we're going to have to think about that. Right, so the idea, we want to use this Brownian bridge, and we want to keep track of sort of the magnitude of this term. Effectively, that's what we'll end up seeing. And the sort of, layman's idea is if the Brownian bridge had to do a lot of work, then the vortex states weren't very good estimates. So you're probably far from the truth. Because we're not sampling from our pi underlying distribution, we have to account for sampling with these bridge paths, right? So I'm going to denote these bridge paths as pi tilde, samples from pi tilde. And this is sort of goes back to when I talked about importance sampling last week, that if we do Monte Carlo, drawing paths from here, we have to correct, right, with the original distribution over the bias distribution. So that's the term we're going to see. Right, so this is our path. So this is including all the dynamics that aren't the Brownian bridge, all of the drift that's not the Brownian bridge. So this is effectively our noise process. And here's the process we actually sampled from with the Brownian bridge. And so what's going to happen here is the Brownian bridge is going to force us to the surfacing location. So in some way there's no observation error, and where your likelihood comes in is really this term, right? We can think about this likelihood is how much do we have to push to keep on the sort of close to the true path, right? And if we didn't have to push at all, then that was a very likely event, right? So these, and think about it in the same way. Okay, so these next three pictures are the same seed, so they're the same truth. So truth is this sort of thick black curve. Here's our observation of truth, the surfacing location. And this is without any Brownian bridge, nothing. This is just what the particle filter sort of out of the box would have done. And of course we can see many of the tracers wandering off, or many of the particles wandering off. Here's what's going on with the Brownian bridge, and this doesn't look very good, I think. So it's a little hard to see here because there are 100 paths or so, but they're basically overshooting the target, and then they know they have to end up here, so then they come back, right? And in some sense, we're still, when we correct for this, we're still sampling. When we correct with the likelihood ratio, we're still sampling our distribution. We're just sampling incredibly unlikely realizations. Each particle that's orthogonal to the direction of the dynamics. The idea being that we don't really want the Brownian bridge to push us in the way the dynamics are already going to push us, right? So that was sort of causing this overshooting, perhaps. But if it's wandering off in a different direction, sort of away from where the dynamics should push us, then we're going to push it back a bit toward the target. And this we can see we get sort of much tighter paths and many paths that end near where we want them to. All right, questions? Okay, so this is sort of the story. There's a lot to do here still. So I have not really finished testing this or done thorough computer experiments. Of course, you're looking for cases that break what you're trying to build. That's always important. And I think there's a lot of other possibilities. There's probably better choices of this nudging biasing term, although I think this sort of Brownian bridge is a good start. I think maybe the model I'm using isn't a great model for what I'm trying to do, because I'd really like to somehow include a variable or a parameter where I have the whole time series, like I would have from the glider. Right? It's not going to have position attached to it, but maybe somehow I could infer that data. I think I'm looking for a different toy model. And Lenny mentioned to me when we were discussing it, perhaps one glider surfacing is really not enough information to identify these dynamics, and maybe we need a cluster to make progress on this. And that's it. Thank you. And this work is supported by a grant from the DoD, the Office of Naval Research. I should thank them. So you're updating, if I understand your question, maybe I don't, but you're updating this, so I should have been more explicit here. This is sort of the end time, your observation time here, and this is the time you're currently at. So, so when you're sort of far away in time, the corrections aren't that big. This term is going to be bigger, so your correction will be smaller in some sense if you're close. As you get closer, obviously if you're far away, this correction is going to get very big because the time is going to get close to the observation time. And this quantity is, I have no proof to show you here, but in a textbook you can look up that this is actually a well-behaved thing. It doesn't, you have to be careful with it numerically, of course, but that thing converges. Mm-hmm.
Where you want to transport or control to some specified target, and you want to minimize so that the distance from that target.
Right, yes. Yeah, no, I think that would be relevant for sure. Yeah.
Also, I mean, you have a choice of the scale of being achieved, right?
But this is sort of the scientist's decision. I want to investigate this part of the ocean. So for I guess for the toy experiment we're coming up with, of course we're choosing it, but ultimately there's going to be some objective in this choice of A to search some path specifically. Right.
So it seems like that you could have a coefficient in front of the A and a coefficient in front of the Brownian gradient.
Yes, I think you could. Yeah. No, and I actually think. I mean, sort of playing around with it, I've been doing things like that, but I haven't.
Because you got, the Brownian bridge, you've got no way of controlling the strength of the Brownian bridge versus the velocity field itself.
Mm-hmm. Yeah, I mean, perhaps that's the problem to be optimizing is how much should you be pushing it in those directions. I mean, I think ultimately maybe this is what you were getting to is there's probably an underlying control problem, which really means you should be shifting the z's a little bit, and that's what I'm interested in, but I don't know what that looks like right now. Miss distance? Okay.
Thank you very much.
Thank you.